In the previous lecture, we discussed about the drawback of a ripple carry adder. We saw how the ripple carry adder consists of a chain of individual full adders, and therefore, at every stage of addition, while the two bits from each of the numbers to be added are always there, the other input, the third input for each full adder is nothing but the carry from the previous addition, and that takes time. That carry bit takes time to be generated. So therefore, due to this chain reaction, that time requirement essentially skyrockets, and as the number of bits in the addition increases, the time delay for the carry bit at every stage also increases. We saw this towards the end of the previous lecture. At that time, I had also asked a question that now that we understand how crucial that delay is, or how critical that delay is, can something be done to reduce the delay from stage to stage? Okay, first question is, can the delay be made zero? Can the delay be made zero? Answer is no, it cannot. It just cannot, because any logic function that you do consists of logic gates. And as I mentioned towards the end of the previous lecture, logic gates are never ideal. Every gate takes some time after receiving the inputs to generate the output. So the delays can never be made zero. But can they be minimized? We can definitely try to minimize the delay. We can definitely try to minimize the delay. How? We can try to minimize the delay by sort of reducing the dependency on the previous stage. Reducing the dependency on the previous stage. Well, let's see how. Where Ci is the carry at the ith stage, or carry generated at the ith stage. So therefore, we saw that since this is the villain, we could represent Ci as a logic function ai bi plus bi Ci minus 1 plus Ci minus 1 ai. We can just rearrange some of these terms and show that this Ci is actually ai times bi, and now in the second and third term I will take Ci minus 1 as common, and in bracket I will get ai plus bi. This is what is there. Now, this is nothing but the carry out at ith stage, or the ith fa. Ci minus 1 is the carry out at I minus 1th full adder. So, this is the expression which we are considering. What we see is this expression is nothing but a small modified version of the previous expression. So you may ask, what is the big deal? What is the big deal of having written the Ci expression in this manner? Right. So the reason for writing in this manner is because it gives us certain ideas, certain insights. Now what we are seeing over here is we have one product term of ai and bi and another plus term of ai and bi. So let's say term 1 is this one, which is ai times bi, and term 2, let me call this as term 2, which is ai or with bi. Now ai and bi, or rather I should not say this, I should say this times ci minus 1. This ai and bi are inputs to the ith stage full adder, and as I mentioned in the previous lecture that these bits are always there. There is no delay involved over here. The only villainous variable is ci or ci minus 1. Okay, so now I can say if ai and bi are both 1, suppose if ai and bi are both 1, what will be ci? ai and bi are both 1 means this term 1 will become 1. So therefore this 1 when ORed with anything will become 1. So therefore one thing I can say is that if ai and bi are 1, ci will be 1 irrespective of what ci minus 1 is. If ai and bi are both 1, ci will always be 1 no matter what ci minus 1 is. So therefore I can say then ci will be 1. In this case ci minus 1 does not matter. So what have we done? We said we identified one case, that is when ai and bi are both 1, that is the inputs for the present stage full adder or the ith stage full adder, and if they are both 1, I can say that it does not matter what the previous carry out is. I don't need to consider it because ci will be 1. So with this I have reduced, no matter by what small a margin, I have reduced the dependency of ci on ci minus 1. So this does not matter. So therefore, in this case, we are saying that our full adder itself in the ith stage is generating a carry. This is called as a carry generation term or GI. So GI is called as ai bi. It's called as carry generator. Only in this case, when ai and bi are both 1, we have reduced the dependency of ci on ci minus 1. So in this case, all I need is ai and bi. So therefore, the delay that is needed to consider ci minus 1 would be reduced or would be nullified actually. Therefore, we will define this term called as GI, which is the carry generator term. Now let's come to this term 2. Now let us come to term 2. Now suppose when we are looking at term 2, what will be the effect of term 1? We saw term 1 is a very powerful term in the sense that when ai and bi are both 1, the term 2 does not matter. And term 1 matters when ai and bi are 1 only. So therefore something tells me term 2 should be considered for cases which are other than when ai and bi are both 1. Okay. Because ai and bi are both 1 we've already considered in term 1. So term 2 we will consider other values of ai and bi. Now when ai and bi are both 0, what will happen? When ai and bi are both 0, term 1 does not matter, even term 2 becomes 0. Because all of 0 and 0 is 0. So therefore there is no carry. So one trivial case, another trivial case which we can rule out directly is that if ai and bi are both 0, then ci is 0. That is no carry. So therefore again in this case, we have reduced the dependency of ci on ci minus 1. So therefore even in this case it's not needed. Now with this we have seen two terms when both are 0 and both are 1. Now there remain two terms when either ai is 0, bi is 1, or ai is 1 and bi is 0. So in this case, the fun comes. In this particular case, when either of the inputs to the present ith stage full adder is 0 1 or 1 0, then in that case ai plus bi becomes 1. ai plus bi becomes 1. So therefore this one when ANDed with ci minus 1 will be nothing but ci minus 1. So therefore in this particular case ci minus 1 will stay. Of course notice term 1 will be 0 because ai and bi, one of the inputs is 0. So then in this case what will happen? In this particular case I can say that ci will be equal to ci minus 1. So this is the case when the carry from the previous stage will be nothing but the carry in the present stage addition also. So therefore in this relation where the previous full adder's carry output is becoming the present stage output, this is called as a carry propagation. And this term ai plus bi is called as pi, or that is nothing but ai plus bi, and this term is called pi because it's called as carry propagator. Carry propagator. So now, what we notice, we have sort of isolated the conditions when the carry in the present addition will depend only on the present inputs versus those when it will depend on the previous carry. Now we have defined two new terms. One is called as a carry generator term. The other is called as a carry propagator term. What we notice is gi and pi are both functions of the present inputs. none of this is a function of Ci minus 1. So, although it does not seem as though a solution, 100% solution is reached, we can say that yes, under some cases, we have been able to sort of isolate the cases when the requirement or the dependency on the previous stage will be there versus when it is not there. Okay, so therefore let us try to see if we can apply this to design the carry of a n-bit adder. So therefore let us consider I equals 0, that is the 0th stage addition. So therefore I can say C0. Now I will put I equal to 0. I will say C0 is nothing but A0 B0 plus C minus 1 times A0 plus B0. So in other terms, this is nothing but G0 and this is P0. So therefore this is nothing but G0 plus C minus 1 times P0. Now, how can we represent the C0? Well, let us try to represent using G0 and P0. So therefore, in stage 0, there are 3 inputs, A0, B0 and C minus 1. C minus 1 I will show, but A0 and B0 we can show in this manner. This is A0 dot B0, which is nothing but G0, and A0 plus B0, which is nothing but P0. Now P0 has to be ANDed with C minus 1, which is the third input, which is usually 0. This gives us P0 times C minus 1, which has to be ALLed with G0. So this is what we will keep. And this output is C0. Now let us ask ourselves, what is the new delay? How many stages are there? From input to output, how many stages do we see? This is stage 1. This is stage 2. And this is stage 3. Well, this seems to be worse. Earlier, in the case of the normal ripple carry adder, we saw that the carry of each stage, or each full adder, had a 2-stage delay. But now we have a 3-stage delay. So this seems to be worse. But wait, let us not jump to conclusions so quickly. Let us not get depressed so easily. We have seen what happens when I equals 0. Let us now see what happens when I equals 1. Let us say, let's consider I equals 1. Let's write the carry 1, which is equal to G1 plus now C0 P1. Now comes the fun. I can write P1, I can write C0 in terms of the ith stage values. So this is nothing but G1 plus G0 plus C minus 1 P0 times P1. And this will be equal to G1 plus P1 G0 plus C minus 1 P0 P1. So therefore, let us quickly draw the stage 0 and stage 1 side by side. So this is on the right hand side. Let us draw I equal to 0, which is a repeat of what we have already drawn. So here we have A0, B0, and here we have also again A0 and B0, and we have a C minus 1 from the side. This is my G0 and this is P0. Finally, we will have one more OR gate to combine and get C0. Now notice what is C1. There is not a single term of C0 anywhere. So therefore this C0 now becomes independent. So with this, let us try to draw what happens for ith stage. Now ith stage, we have these three terms. Now we have these inputs A1 and B1. So again we will have an AND gate which will generate G1. So this term is done. We will need one more OR gate to generate P1. Now we need P1 G0, but we already have G0 from here. So therefore we will need one AND gate. Let us say I am bringing the G0 from here. This will give me P1 G0. This term is also done. And finally, we need this P0, P1 and C minus 1. So one more AND gate, let us say. So this one will come from here. C minus 1 comes here. P0 from here, we can get it. And P1 is over here. This is what we get. Now this term is C minus 1, P0, P1, this is also there. Finally, we will need one OR gate to combine these three terms. So one over here, the other, we get C1. Now, what do we see over here? For the I equal to 0th stage, we see a 3-stage delay. when looking from the input to C0. But now let's look at I1. Let us look at C1 compared to all the inputs. When I look at A1 and B1, again the number of stages are 3. But that's not enough. We have to consider the carry also. Notice that there is not a single C0 which is coming. It is in terms of C minus 1. So if you consider C minus 1, this is coming over here and the number of delays is now 2 stages. So 2 stage delay for C minus 1 here also, and for here also there is a 2 stage delay. So worst case is again a 3 stage delay because of A1 and B1. Now we were getting very depressed just by looking at the I equal to 0 stage where we saw a 3 stage delay. But when we saw for I equal to 1, we are seeing that even there the worst delay is of 3 stages. Nothing more than that. A1, B1 and C minus 1. All of them, the worst delay is 3 stages. Stage 1, stage 2, stage 3. Which is why I have also drawn the gates in such a way that they look like stages. So this is indeed very, very encouraging. Both in 0th stage and 1st stage, the number of delay stages are the same. So suppose we say the delay is 3 TD over here. Or let us say the delay over here is TD due to 3 stages. Here also the delay will be TD. Nothing more than that. There is no linear increase now. Now what about for higher values of I? What about for higher values of I? So for I equal to 2, we will see C2 equals G2 plus C1 P2. Now C1 will be what? C1 I can write it in terms of as G1 plus C0 P1 P2. Again in a recursive manner I can write C0 also G2 plus, but first let me open this term up, G1 P2 plus C0 P1 P2. Now this will be G2 plus G1 P2 plus P1 P2 will be common and C0 will be G0 plus C minus 1 P0. Finally this will be G2 plus G1 P2 plus P1 P2 G0 plus P1 P2 P0 C minus 1. So now if I were to draw this stage, of course the logic diagram will become a little bit more complex, but nonetheless let's try it out. So here we have the inputs A2 and B2. This is G2, this is done. Again we have one OR gate for A1, so A2 and B2, which is P2. And the G1 from the previous stage will come. And this is G1 P2. Again P2 is over here P1 from the previous stage will come over here, and G0 from the previous 0th stage will also come. This is the third term, and so on and so forth. Again, you will have one OR gate to combine all of these. You will have one more for the fourth term, but which I am not showing. Once again, you will see that the worst case delay is just 3 stages. So, what are we seeing? We are seeing that irrespective of the value of I, the number of delay stages remains pretty much the same. In case of a normal ripple carry adder where the carry is propagating in terms of a chain, the delay in each stage is increasing linearly. TD, 2TD, 3TD, and so on. But in this particular configuration, what we are seeing is that by making use of these two new terms, that is called as a carry generator and a carry propagator, we are able to express the carry of each stage not as a function of the carry of the previous stage, but as a carry from the very first stage or the 0th stage. And of course, the other inputs are AI and BI, which are not dependent on any other stage. So therefore, the number of delay stages per stage of addition remains the same. So therefore, the delay in generating the carry at each and every step remains the same. It does not increase. So therefore, no matter how many additions you are doing, how many bit addition you are doing, the total delay will now not be n times TD, but instead it will be TD only. So therefore, this kind of adder is a fast adder. And this technique where we are essentially achieving fast addition by trying to predict the carry using the GI and PI terms, we are trying to predict the carry. This is called as a carry look ahead adder. Look ahead means we are trying to look ahead in time, something like that, and trying to obtain what the carry is without depending on the immediately preceding stage, but rather using the very first stage of addition, which saves us a lot of delay. What we notice over here is that, of course, in ripple carry adders, the number of gates used are much less. You can realize the carry function using, let's say, 3 AND gates and 1 OR gate. But here the number of gates needed increases, but the number of delay stages does not increase. So this is one of those classic examples where we are increasing the complexity in terms of gates to achieve something better. So therefore, this is something you should be able to appreciate. What is that thing? The thing is, it does not always mean that less number of gates is always better. No. The classic example is the ripple carry adder, where we saw each carry stage needs 3 AND gates and 1 OR gate, but in that case the delay increases significantly. But over here, in case of this fast carry look ahead adder, we are trying to generate the carry using the present bit inputs AI and BI and the previous stage or the first stage carry, not the previous stage carry. So therefore the number of gates increases. This is not the most simple solution, but the number of delay stages are less. So therefore it is a faster circuit. So therefore, in your digital design career, you may often come across circuits which look very complex but are faster. And there are circuits which you may see which look very simple but may be slower. So with this, we come to the end of discussion on combinational logic circuits using MSI blocks. We shall continue in the next lecture. Thank you.